Right.
So welcome everyone to our weekly seminar from the MCFAM, the Minnesota Center for Financial and Actual Mathematics. Very pleased tonight to bring to you Professor Gerald Wang from the University of South Dakota State University. He is a Dubois Professor of Business and Finance and Investments, and he holds a PhD from Florida International University, and also is a CFA charter holder. And his expertise is in the areas of asset pricing, financial and community derivatives, volatility, machine learning, market microstructure, non-Gaussian distributions and processes. And not surprisingly, I noted from looking at your background, Professor Wang, and being at South Dakota State, that you've written a lot of papers on commodity markets. So that's probably not a big shock. That would be very topical for you. So, but volatility surfaces are interesting to lots of people and lots of markets. So this is going to be a very germane conversation. So I'm just going to turn it over to you.
Thank you very much, Gary. Really my pleasure to be here to talk about this research that have been more or less ongoing. I'm going to share my screen just in a moment here. Let's see if I can make it.
And I'll just interrupt real quickly and point out that if you have questions, you can put them in the chat, or you can send them to me privately as well. And I will try to manage those for the end.
Right. Let me see if I can, hold on. It's been doing this for me today. Somehow it was switching around the, right. Is that good?
That looks good.
All right, thank you. So the title of this research is multi-step forecast of implied volatility surface using deep learning. And this is originally based on my master student's thesis. And I have been always interested in basically options pricing, volatility, VIX, implied volatility, the modeling of that. We thought of many different possible topics and eventually boiled down to this one that is more manageable than say option pricing using deep learning while dealing with all the time aspects. So this is more manageable research using implied volatility surface. So that's how we get to this this particular topic. And so I'm gonna just move on. I heard some of you may not be know much about implied volatility surface. So I'm gonna just quickly go over kind of at a very high level of what is the implied volatility surface and why it's important. And implied volatility surface is based off stock options, and in this case, particularly S&P 500 index options. So for those who may not be very familiar, stock options is just right to buy or sell stocks at a predetermined price in the future, right? That predetermined price is called exercise price or strike price. And then another aspect is there is the expiration date in the future. Right? So put it in a context of a very abstract relationship, is the option price basically is a function of implied volatility, which is the most important input. And basically traders mostly trade off the implied volatility. And that's one. And then there are some other fundamental inputs like stock prices and strike price and maturity. And so if you invert this function, implied volatility as a function of the stock price and option price, and then exercise and maturity, then you can construct what I call the implied volatility surface, mostly as a function of strikes or exercise price and the maturity or contract month. So you can imagine a 3D surface of implied volatility, which usually expressed in percentage terms as a function of strike price and the maturity. So I'm going to show you a graph so that you have some sense of what the implied volatility surface is about. This is actually the average implied volatility surface over the sample period that we studied from 2002 all the way to the end of last year. You can see there is a on this 3D graph. If we say the vertical axis is the implied volatility, the horizontal axis on this axis is what we call log moneyness, or basically strike relative to the stock price. And there is, by and large, there's a downward sloping shape, and that's what we call the implied volatility skew. Basically, so this 0 point, it is at the money, and those negative ones are what we call out of money put options. And so usually have higher implied volatility than, and this to the right of it is implied volatility for the call options, out of money again. And you can see a little bit also along the expirations, and longer maturity has slightly higher implied volatility. That's what we call contango in the volatility. And that's, again, this is the average shape of it. So, and any day this shape could be very different. In a moment, I'm going to show you something as more recent, but you kind of get a sense of it. It's a 3D shape, is not like very regular, has very nice picture or smooth, and not at all, right? So that's why it's kind of interesting. So I'm going to just kind of give you, this is a very quick intro to what is the implied volatility surface and how it actually looks like. And the agenda here is I'm going to talk about what I'm actually doing, we are actually doing, and how we contribute to the literature, and why it is an important topic, okay? And talk about literature and what data we use, what methodology or models we use, and eventually conclude to give you some results. Here, and why it is important. I just mentioned the stock options, index options, and you probably don't know how giant this market is. Here, this is S&P 500 index options, the daily volume for the last 10 years. That's basically, I'm using the CBOE data. You can see the calls and puts trading volume, daily trading volume is around 500,000 contracts to most recent over 1.5 million contracts, right? So if you translate it to the dollar amount or daily notional value on average, and you can see the graph again from early 2000 to 2018, that's where we can have the notional value basically based off the CBOE's data. It is over $390 billion of daily notional values, right? So it's kind of like nominal value of those contracts is worth this much, and that's changing hands every day, right? And here, so we see the daily trading volume is huge, and also you can see the this is the surface that is changing. Just give you some snapshot. The first one here is just end of last year. You can see there is little, just like what we saw earlier, there is a implied volatility skew. Actually, it's more of a smile on this one here. Basically, the implied volatility has higher level for out of money put options, and also a little bit also for out of money call options, a little bit high as well relative to the at the money, right? And so this is kind of more typical implied volatility curve or surface. And then this is the 2000, and this is this year, just right before the COVID hit. the volatility level is, VIX level is around 14, right? So it's very similar to what we had in at the end of last year. So this one is March the 23rd. That is when the market bottom. So the level of the VIX is 61.6. And also you can see the at the money volatility is 108. That is a nearby at the money 108. That is, of course, it is just part of the VIX. And you can see how high that is, very, very, very high. And it's more than, 8 times, 7 times of what we typically see, at least for the past 2 years, right? And then this is right now, the level is still relatively elevated. And you can see the shape is all different and it's changing every single day. And that makes it a little bit challenging to model the whole surface throughout the time, right? And so that's what we set out to do. Again, just to recap, it is important because it's a huge market. Everybody looks at the S&P 500 index and options and also the volatility of it, right? And it's also stochastic, and hopefully I give you enough picture to prove the point. This is a non-trivial question. And so what we try to do is predict this surface using deep learning techniques, right? So it's not like this is the brand new, nobody has ever, has never looked at this implied volatility thing. Like one example is Calkin and DAS in 2017. They used the neural network to basically fit the option prices and essentially fit in the Black-Scholes models. They are more of doing a simulation to see if neural networks can actually fit non-linear functions, right? So they prove that this is working. But of course, is a different thing. We're talking about a time series prediction of the whole surface, 3D surface, right? That's what we different from them. And also the neural networks that we use are completely different. They are using more traditional neural networks or the basic neural networks. We're using the deep learning neural networks with convolution network and LSTM combined together, right? So that's our contribution. Just to make it clear, this we mentioned, there are some others. Liu et al. In 2019, they also proved neural networks can fit not only the Black-Scholes, the classical Black-Scholes model, but also the Heston pricing model. So they're more concerned with pricing formula than predicting the surface, which we think is more relevant in a way for the trading purposes, right? And also Hasker et al. 2018, those are the pretty new papers. They used the recurrent neural networks and LSTM to predict VIX futures. This is similar, but then the VIX futures, it is just one single observation as opposed to our implied volatility surface, which has a 3D, both strikes and the maturity as the part of the surface, right? So in their case, is basically the volatility term structure, just one observation there, okay? And related, and basically the motivation of using the what we eventually adopt for this deep learning framework was this 2015, they applied convolutional LSTM model to weather forecasting. So I'm going to make this analogy and why we actually eventually think this probably is a good idea to apply to implied volatility surface. Think about weather forecasting over time, not a static one shot of weather forecasting, but weather forecasting over time. And weather forecast is basically you need to take the you know, the heat and all those, the temperature and the wind speed, those numbers, and that is basically on a map, and that is, or colored map, and that is multi-dimensional inputs and also multi-dimensional outputs. And in a way that is similar to the situation that we have here. We have the strike volatility as a function of the strike and maturity. And so that is a 3D surface, and that's kind of the analogy that we're thinking of, you know, the pictures, and that is moving through time, right? So that's why we think this might be a useful technique to apply. And so that's kind of the idea. And you can see what we do is different from what everybody else do in terms of predicting the volatility surface. Instead of either cross-sectional fitting of the option price data, and that's what we are different. The other is we are predicting over time for the whole surface instead of just one observation of volatility, okay? So the data that we use is CBOE's daily S&P 500 index going from 2002 all the way to the end of last year. My graduate student used a tiny data that I originally had that was just basically 2 years worth of the pilot data. So I later I updated all this all the way to the end of last year. And this is a pretty big data. And with 52,000 unique contracts, basically combination of the combination of contract month and the strikes for over 4,000 days. And because this is raw data, is not easy to work with. So we have to kind of normalize a little bit, and we downsample to quarterly expiries, quarterly contract month to make it more feasible to work with, right? Eventually we get to 9,000 contracts. And the data, after we actually process and clean it up, not completely clean up, is over 1 gigabytes. And then we use some other like spot price data and interest rate data to find out implied volatility. And this implied volatility is really what we call the Black-Scholes implied volatility. And this is just a conversion from the option price to implied volatility. That's what we are working with, and that's what we are predicting. Right? This is a lot of people probably underestimate the amount of work here. The filtering and the reformatting the data takes a whole bunch of time, and it's never trivial. So the first step is, because we get the raw data and we process just computing Black-Scholes implied volatility using Black-Scholes formula, and we use the package, Python package, to back out those implied volatility to make sure that it has very stable, reliable results. And then we downsample. This is the total number of original data is over 8 million contracts. So what we do is, as I mentioned earlier, kept the 4 expiries, basically 4 most commonly followed, the March, June, September, and December contracts, right? And then we have ended up getting those on any given day would be those many contracts that we are dealing with. And then the other step we try to clean or downsize the sample is to have this implied volatility put it into the bins, right? Using the strikes log moneyness and put it into bins instead of just all single strikes, because you know the strikes we're talking about, couple hundred, 300 strikes, and that is way too much, right? 300 times 4 would be way too much to deal with, and maybe doable, but we haven't actually tried. We just tried initially to use this 20 bins, and then we interpolate those implied volatility to get slightly smoother surface to work with to train the neural networks, right? So in the end, we have this continuous time series of implied volatility surface. So that surface is basically implied volatility with 20 monotonous cohort and 4 contract months, right? You can think of that as 1 for any given day. You have 20 by 4, basically 80 observations. For any given day, you would have that much, right? So we interpret it if necessary, if there is somehow there is not available, some implied volatility is not calculated or some missing values, then we do it this way, right? In the end, we have over 4,000 training sample and left this last 3 months as the completed out of sample or test data to check if the model actually works out of sample completely. Right. The methodology that we use is basically we try to benchmark against the classical time series models. So the idea is just use the historical implied volatility surface data to predict future implied volatility surface. And we're not making it very fancy, just historical implied volatility surface to predict implied volatility surface. As we know, volatility is very sticky, and that tend to be very persistent in general, at least in short run, right? So we use vector autoregressions, as you know, is 80 sample points at any given point in time. And since, as we know, all those implied volatility observations are probably very closely related, and we tested they are integrated at integral of order 1. So more or less, there may be some unit root, possibly unit root there. So we consider vector error correction there to account for possible co-integration among those time series, right? Because anyway, they are all derived from the same underlying S&P 500 index. So that's the benchmark. And then we use the most traditional one, the time series model. Deep learning for time series would be the long short term memory models, LSTM. But this one is what we call a fully connected. So we treat all those 80 observations independently, put them as just independent variables to forecast and make no connections. Or is not making no connection. Do not utilize the connections between the strikes and the maturities, right? Strikes are strikes and maturities. We don't try to model the relationship among those. That's the traditional LSTM model. And then really our contribution is here is the convolutional long short-term model neural networks, right? So this will take into consideration all those possible relationship between the strikes and maturities. Okay. Just for those who are not familiar with the LSTM framework, we need just throw the kind of math formulas there. And I assume mathematicians tend to like this better than the graphs. So here the idea is LSTM models that you take input, those are your input data X, and you are going to use whatever observations. In this case, our observations would be, or the output would be our implied volatility, right? So this would be historical output or yesterday's output, implied volatility here. X would be the whole surface, right? And then we have this so-called forget gate. We decide how much we keep the information from the past or the input, right? And then there is the input gate that is to tell you how much state variables that you're going to use. This is the input gate. And then there is a state variable that's when we need to come up with the new information from all the say the past observations, the output, and also the input variables or the features to decide what kind of state we might want to use to update the state, right? You can think of any kind of filtering problem, and that is you need to have some new information that you need to sort of embed in this prediction. And then you need to have some cell gate or the state, which is the old state variables. And you decide how much you need to keep or how much you want to forget. And then you bundle them together to generate a state variable. And then you use the output gate to control how much and using the state variables to produce or to predict or produce your output variables, right? So that's kind of the idea. And you probably see a lot of these graphs, and that's basically representing all those functional relationships, right? You have this here, this Z is really the state variable here, C. And then you input, you combine them to decide what you want to put in as the new state variable. And then you will use the forget or forget gate, decide how much old state you want to put it in. And this is new state, old state combined to generate the new state as the input. And eventually you use the output gate to kind of decide how much you would have in producing your output. So that's kind of the general idea of this LSTM framework. And in our implications, we use the 3 hidden layers, and this is the art part of it. And there is no single formula or exact science to tell you how exactly you should do, right? We use the most popular one, couple of hidden layers. In this case, we use the 3 hidden layers. And remember, we're just treating those volatility series as independent. Remember, that's 20 strikes, 20 bins of strikes, and 4 maturity contract months, right? They are independently used to as our objective to predict. And we use the 128 neurons in the first hidden layer, 64 for the second hidden layer. And then in the last one, we just flatten out and to eventually produce the output layer. That's what we produce, basically implied volatility. And in between the layers, we use a 25% dropout to avoid the overfitting in general. That's the kind of the structure of the LSTM framework. And then the convolutional LSTM model is very much like LSTM model, but then you are adding the convolution layer of it. And for those who might know a little bit of convolutional neural network, basically what you do is you are taking different filters. You can think of that as a lens of different size. Think about in the, like if you are trying to recognize a picture or some patterns, and then you use the filter to shine through all those data and to figure out what are the structures or some of the features, edges, or something inherent in the data. And so you use those filters to shine through all those. Hopefully you can pick out some important features. And this is what motivates the paper for the weather forecasting and using the convolutional network, right? So it's just kind of like you are trying to figure out the picture, is the edge, this is round, or is some sort of shape. And if you use the filter, and you can pick out those important ones, features here. And this is a model we run. You can see a gigantic number of parameters you need to estimate. Use again 3 layers of 3 hidden layers, largely 3 hidden layers, and in between we have some of the average pooling layers to kind of reduce and again simplify between layers. right? So the first layer filters, you can think of it as 16 squares that you're going to shine through. And then the next layer is we're going to use the 8 filters. Since we are going to assume that we're going to pick out some of the important ones, later on we can use the less amount of the filters to figure out the features. And then in the end, we're going to just flatten out, just like a fully connected LSTM model, the traditional LSTM model. And that's the structure. Really, what really is most important is, which I highlighted earlier, is when you use this filters and allow the grids that has the feature of both implied volatility as a function of the moneyness or the strike and the maturities. And that's when we are going to make all these connections and let it just go through all the possible combinations instead of treat them separately. Moneyness, like implied volatility as a function of only moneyness, implied volatility as a function of only maturity, right? That's really the key. And that's why we think this convolution network is more helpful in picking out the relationship. And in other words, modeling the whole surface as a whole instead of just separately, right? Again, this is the filters I actually have. Probably duplicate the same slides. Here, this is in and out of sample errors for the data we used. The in sample, as you see, they can for the vector error correction, vector order regression model and vector error correction model, they do just fine. And the in sample, it fits seemingly okay, and 5% error. LSTM, and it has lowest R root mean squared error, 0.014, and which represent of 3.5, 3.6%. This is the lowest among all. And a convolutional network and has also low in-sample error. So in other words, those kind of, all those traditional classic models and the LSTM models seem to fit the in-sample relatively okay, right? And out of sample, that's where the difference is. And root mean squared errors are not so bad, and the vector error correction and the classical time series models. And really what we see here is the convolutional network is significantly lower, and 8% of errors. And this is kind of surprised myself as well. I tried many different times to make sure that our results are robust. And it is. And if we can generate 8% of out of sample errors, and that is very, very impressive, because I worked on the implied volatility forecast and the VIX futures forecast, and it's very hard to generate out of sample that low errors. And here, this is just smooth and really not of interest to us. Basically, we want to see the conclusion is the convolutional network with the LSTM is better than others, right? And this is a time series for the last 90 days of the results. And you can see from the graph, and it's rather obvious. The last one is the convolutional network and fit pretty well, except the last, couple of days, especially in December, right? Basically, none of them fit the December well. This is purely out of sample, okay? Here, this is another way to take a look at the results out of sample again, just to see just simply 1 day forecast. Root mean squared error is 0.01. Just so you know, the VIX, not the VIX, the volatility at the magnitude of 0.16 on average, about 0.16 historically. So 0.01, that is about 6% or so, right? So this is the mean absolute percentage error. This is 6.6% and 8.6%, and so on and so forth. This is out of sample. What we are more interested in the LSTM model, is not so well, and this is what we think probably is there is some overfit, and there is shortcoming of not using the relationship between again strikes and maturities. And the most impressive one would be the convolutional LSTM model. The error is anywhere from 4.6% to 83%, right, out of sample, going from a 1 day out of sample, 30 day, 60 day, 90 day out of sample. And you need to take it with a grain of salt, especially for the 90 day out of sample, because we are not observing too many of those for the 90 day. And more relevant ones would be the first couple of predictive horizons, okay? So that, and we also look at the out of sample errors across different contract months, and in particular across the strikes as well, okay? And you can see largely, and obviously the difference is clear that the convolutional network is the best among all. You can highlight here, they are pretty consistent for the first 3 contract months, and from anywhere from 3% to 7, 8, 9%, but then jumped up to 16%. It's all big numbers, large errors, relatively speaking, for the December contract. And this is what we think is going on, because we are basically using the last 3 months as out of sample. And so that means it's October, November, and December. So when we get to the, the December contract, for some of the tradings, and the December contract is really not the most nearby December contract, but rather the next year's December contracts and the further out December contract, because some of them will expire somewhere there, right? But for those March, June, and July, and June and September contract, there is no shift of the contract month to the next year or the following year's contract, right? So that's really basically what I'm saying is unfair to use the December contract unless we extend out the test data to much longer, and which we plan to do. And we will probably won't see so much of a spike just for December contract. That's basically the nature of our test sample, is really near the end of it, right? So that's our conjecture. So the conclusion is here basically. It's very clear that the convolutional LSTM model works pretty well. Out of sample, the worst out of sample is 8.3%. And for a lot of those, actually is about 3%, and that's super, super good. The traditional LSTM model actually fit in sample very well, but out of sample kind of deteriorate that is performance, okay? So we think this is probably an overfitting problem, and also lack of the structures between, again, I'm repeating myself, between the maturities and strikes, okay? And the traditional time series model, they actually do okay in sample, but out of sample, it's not as good, 13%, 13 to 14%. Right. I also mentioned the convolutional network that has roughly pretty stable sort of performance, other than the last contract month, December, which I mentioned probably because of the data, that's test data that we used. Okay. And a side note is like co-integration. Statistically speaking, we test for a co-integration, and it is there, but when it's used to model, when we consider the co-integration in the vector error correction model, really doesn't help so much relative to vector autoregression model in terms of predictive ability, even though it's statistically significant, but it's not so important for out of sample prediction. That's what I have. Some other things, further research and just to see is what we are considering is expanding the range of the strikes to consider way more out of money, and also the contract months, not just the 4 contract months, possibly to 12 contract months, because S&P 500 index option actually actively trade across most of all contract months. And the reason why we picked only 4 contract months is purely because of a computational cost, and it's very expensive to. You can imagine we have tens of thousands of parameters to estimate for the convolution network. Now you have all these contract months, 12, and let's see times 100 strikes. That is how many magnitude? I don't know how many magnitude more of the parameters, and that could be a challenge. But we're still thinking if there is a way of dealing with it. Other things that I've been thinking is consider some other features in this current model. Is really simple. Just use historical surface to predict the future surface. We didn't really include any other additional features that can help outside of the surface, like VIX, leveled VIX. In other words, whether the market is in the crisis mode or in the just normal tranquil period, and we don't distinguish that. And the other one is volatility, which could be factored into this as a feature. That's something could probably help improve the both in sample fitting and more importantly out of sample fitting, especially if we were not talking about way, you know, if it's in the crisis zone or crisis period when the VIX is elevated, and if the neural network knows this is at the higher like level, the uncertainty and volatility, it may adapt a little better. But of course, you can potentially use the historical information like past 30 days or whatever, 60 days to infer we are in a high volatility you know, regime. But maybe using VIX and the VVIX, volatility as a feature may kind of get better to help the neural networks to understand where we are in terms of the volatility regime. And that's just something that I've been thinking about, possibly refine the traditional classic models, right? And that's what I have. Open to anyone to questions or comments.
So there's a question in the chat.
Yep.
And I will read the question, although maybe you can see it. I have a question on the valid time period of the LSTM model. As you are predicting the price of the following 90 days with around 15 years of historical data input, will this estimated performance model perform well after the next 90 days after the predicted time? Do you need to update the model with new data at some period as the model may be becoming inaccurate for further predicting?
Okay, that's a very good question. So far, the results that I presented really didn't update the model at all. So this is why it's so impressive to me. And so basically, once we train the model, the convolution network, and those parameters are sticked in there. So it is the same sort of structure. You can think of the parameters are estimated already. And then we use that to predict next day, 30, 60, 90 days. So we don't retrain the model at all. It's not like a constant retraining. So basically at the end of the training data, we just fix those and use those parameters to predict. So that's what we do. As for beyond the 90 days, we have not actually tested, and it can be easily adapted. Basically, we can adopt this model. Really, the model is trained. Basically, the model knows how to predict, and just matter of have more out of sample data, because basically we have just until the end of the year. That's the data, and if we have more data this year, we could do that too. And I think this is also partly reflect that relatively poor design of the out of sample. We should have leave a little more out of sample for the evaluations, and we can definitely do that. And actually, we can use less training data, to predict, to have more out of sample data. And so that's how I would answer.
Thank you. Next question is, why use dropout to avoid overfitting rather than using regularization directly?
The issue is with the deep neural networks that you have just way too many parameters, in the sense that is almost worrying. And a lot of people criticize the deep neural network is a black box. Is just, you can easily get overfit if you don't have a drop. And also the other reason is, this is overfit is one reason. The other very important reason is the convergence. When you have, let's see, some of the, when you do the optimizations, you either use the stochastic gradient descent, and that can kind of get stuck sometimes when you have this many parameters to fit. And some of those parameters may not move at all when you optimize. And so when you drop out some of it, and then potentially you can let the optimization algorithm to move on. Otherwise, you may get stuck in some either local minimum. Basically, the mean squared error is the objective function. So that's basically the way to avoid that getting trapped in the optimization procedure.
Great, thank you. Next question from John Dodson. Says, thank you, Professor Wang. I have a question about your comment on incorporating the VIX. Since the VIX is calculated from contemporaneous S&P index options prices, why do you think it would be predictive of the S&P/X implied volatility surface?
Is that the VIX is not really contemporary. If I were to incorporate those as features, I would use the VIX as historical VIX or the past observation instead of the current one. Otherwise, we are just cheating if we're just using the current VIX, obviously. And that's not the right way to do it. Would be the past information. And the VIX is just one way to, aggregate the implied volatility across the strikes. And this is one particular way. I'm just thinking out loud and see if that might stick. But again, this is a good point, not concurrent VIX, but rather historical VIX.
Other questions? I have one. You mentioned about computational costs. So have you addressed this by using or trying to facilitate some kind of cloud computing, or is this a matter of practicality? How did you generate your computing power?
This is a very, very good question, actually. It's initially we were thinking of using just local computers, and like my computer has GPUs, and just use the, we're using the Keras and the TensorFlow, and my student is really the expert in that. And he suggested, and actually we eventually went for that route, is using the Colab. Just basically Google deep learning sort of framework, Colab, and that's what we used. At times I run into problems. He didn't run into the problem because he was using the much smaller amount of data. Later on, I updated all this data for over a decade of the data. So I run into the resource bottleneck. Sometimes they say GPU not available, and getting slow or need to reconnect, that's just the regular Colab. And there is a pro version of it. And also the current version is 2.0 now. I run today is actually a little faster than before. And maybe computation cost might not be as high or as in the past. So yeah, that's what we use, Colab.
Cool. It sounds like you already have the premise of a grant right to get more computational resources.
Yes, yes. Yes, if we are talking about, I don't think Colab can actually handle all those. If I really want to extend to the whole surface with all kinds of all strikes available and 12 contract months, that's a heck of a work, I think. Yeah, we need something else computationally.
Other questions? So we are at 55 into the session. So this is a good point. Certainly we have a few more minutes for questions if there are any, but I certainly want to thank Professor Wang for this really very cool presentation. Very interesting topic, very timely, and I think it seems like there's more work to do, but at the same time, there's very promising results.
Thank you so much, Gary. And it's really great to meet you during at the Data Science Symposium, and really thank you for the opportunity to speak to your peers, and really appreciate it. If anyone has any questions about whatever, right, about the program and how we do things, just feel free to reach out.
Very nice.
Right.
All right. Okay. Well, good night, everybody.
Good night. Thank you. Bye.
Thank you.
Thanks.